in the last lecture, in which we applied photons on one end, increasing the concentration of charge carriers at one end comparing with the other end. And if we plot a graph of concentration with distance x, where x is a distance from one end of the semiconductor to the other end. Now, we are simply assuming that the free electron concentration is a function of x represented by nx. In such cases, obviously, if the concentration of free electrons is more in one part of the semiconductor with respect to another area, then obviously the free electrons where their concentration is more will go towards the direction in which the concentration is less, which results in a current. This process is very similar to the diffusion of gases, where atoms of gases move from high concentration to the region of low concentration, and the current density which results due to this effect is called as diffusion current density, and its formula is given by minus q, which is the charge on the charge carrier multiplied by diffusion constant multiplied by gradient of concentration of charge carriers. For holes, we have positive charge, which is q, and for free electrons, we have negative charge. In the last lecture, we assumed that photon bombardment is taking place at one end, which results in increase in the concentration of electrons. But it will result not only in the change in concentration of free electrons, but concentration of holes will also increase. Let the change in concentration be represented by P naught x. X within brackets is representing that hole and free electron concentration is not constant throughout the semiconductor and is a function of distance x. Diffusion current density for holes is equal to minus q multiplied by diffusion constant of holes multiplied by gradient of hole concentration. Similarly, diffusion current density for free electron is given as minus into minus q multiplied by diffusion constant for free electron multiplied by gradient of free electron, giving diffusion current density for free electron to be equal to q into diffusion constant of free electron multiplied by gradient of free electron. We have assumed positive charge on hole and negative charge on free electron. You can see that the diffusion current density have different signs for hole and free electron, meaning that the net current density will be in opposite directions. When we were talking about the drift current density, where we have the formula N into Q into Vd, where Vd is the drift velocity, and you also know that drift velocity is equal to mobility into electric field, and we also find the value of mobility to be equal to Q into tau divided by effective mass for conductance calculation. Here N is simply representing the concentration of charge carriers. We are not taking any particular charge carrier like hole or free electron. After applying the value of mu and electric field in the drift current density, we will get you can see that the drift current density is actually proportional to the square of charge present on a charge carrier, meaning that even if we take free electron into our consideration, then the charge will be negative q. But since we have to square it, the net impact will be positive. It means that for the same electric field, the direction of drift current density for free electron and drift current density for holes is in same direction. However, diffusion current density for free electron and hole is in opposite direction. If you are still confused, then rather than remembering the formulas, you just need to remember some basic knowledge of electricity. Suppose that we have an electric field like this, and free electron and hole concentration will remain the same. Now, we have four cases. Due to the electric field, free electron will try to move opposite of the direction of electric field. But we know that the current due to the flow of electrons is opposite to its direction. Therefore, it will result in net drift current 2V in the direction of electric field. Similarly, holes will move in the direction of electric field, providing net drift current due to holes 2V in the direction of electric field. Now, if you talk about the diffusion current, then since the concentration of holes at the left side of the semiconductor is more as compared to the right side, due to the diffusion, holes will move from left to right, which will give net diffusion current due to holes 2V in the direction from left to right. Concentration of free electrons is also high in the left side of the semiconductor with respect to the right side. Therefore, free electrons will also move from left to right. But again, as we know that the electric current is opposite to the direction of flow of electrons, therefore the net diffusion current due to free electrons will be from right to left. So we have three components of current which are from left to right and one current component from right to left. I hope this is clear to you because this is very important. This subject, electronic devices, is not difficult to understand, but it is also very easy to commit minor mistakes while solving problems. And this is one such point where students usually commit mistakes in finding the sign or the direction in which current is actually flowing. So be cautious by solving the problems. Now we have net current density to be equal to net drift current density plus net diffusion current density. Net drift current density is given by drift current density due to free electrons plus drift current density due to holes. Similarly, diffusion current density is given by diffusion current density due to free electrons plus diffusion current density due to holes. By putting the value of all these four components which you have studied in this and the last lecture, we will get Now if you see carefully, then there is a minor mistake in this equation. The thing is, in the last lecture, we have assumed that the free electron and hole concentration in the semiconductor is actually constant with distance x. Therefore, we denoted the free electron and hole concentration by N0 and P0 only. But if we assume that the free electron and hole concentration is constant, then the gradient will come out to be 0. So we will have to modify it a little bit such that the equation will become this is the final equation. However, sometimes J net is also written as net current density produced by holes plus net current density which is produced by free electrons, where the net current density due to holes given by the summation of all the components which are produced due to holes which are Similarly, we have net current density due to free electrons to be equal to these two formulas are also important. One simple point of information is that diffusion constant multiplied by gradient is called as particle flux density. Therefore, diffusion constant of free electrons multiplied by gradient of free electron is called as free electron flux density. The same goes for holes. Formula in this particular lecture are very important. Make sure that you are comfortable with each and every formula present in this lecture.